Okay, so we'll now move on to question number 2 in exercise 3E. Okay, so we'll practice with more questions on vertical oscillation in simple harmonic motion. Okay, so a particle P of mass 0.5 kilogram is attached to the free end of a light elastic spring of natural length 0.5 meter and modulus of elasticity 50 Newton. The other end of the spring is attached to a fixed point A and hangs in equilibrium vertically below A. Calculate the extension of the spring. Okay, let's do it. So in part A, you have your spring. The natural length is 0.5. And then what do? We hang a mass of 0.5 kg. So you know the moment you hang the mass, there will be an extension in the spring. Okay. So this is the natural length. And this is E. E is the distance the spring extends due to the weight of the object. The weight of the object is 0.5 g, and at this point we have a tension. So the object is in equilibrium. This is the equilibrium position. Okay, this is the equilibrium position. So the object is in equilibrium, which means the tension at this point must be equal to the weight. So you will write here tension is equal to 0.5 g. Tension is lambda x over L equals to 0.5 g. Lambda is 50. Lambda is 50. Extension, the length the spring has stretched beyond its natural length. I have named it as E over natural length 0.5 equals 0.5 g. And now we'll make the subject equals 0.5 g into 0.5 divide by 50. Guys, how much is E? Point. First we'll get the full decimal. What's the full decimal? Point. 0.049. So we'll leave it at this point. 0.049. Okay. So let's get they're asking us to get the length of calculate the extension of the spring. Yeah. So this is the extension of the spring. 0.049 meters. This is the extension of the spring. This is clear? Okay, so we'll move on to the next part. The particle is now pulled vertically down a further 0.2 meter and released from rest. Okay, so what are we doing? So you're pulling it down a further 0.2 meter from the equilibrium position. Now, do you recall what I have told you about moving below the equilibrium position? I told you now this is clearly the equilibrium position, right? So the equilibrium position, whatever the distance that you move this object below its equilibrium position will become what? Will become the amplitude in your simple harmonic motion. Whatever the distance that you take it below the equilibrium position. So because the equilibrium position is where the object is at rest, where the object would naturally like to be in. So whatever the distance you take initially, the initial distance you move from the equilibrium position will set the amplitude for your SHM. So they are saying they are pulling it down a further 0.2, which means 0.2 meter will be your amplitude. Okay, 0.2 meter will be the amplitude, and they are asking, and they are releasing from rest. They are asking you to calculate the period of the resulting oscillation. How do you calculate the period of the resulting oscillation? To get the period, you need the omega. Periodic time is t equal to pi over omega. To get the omega, first you must always what? Prove the characteristic simple harmonic motion equation. X double dot equal minus omega square. So first you get that equation. That equation gives you the omega that you require. Okay, so shall we get the omega value? Okay, so let's draw the diagram first and mark the object in a general point. So this is the object in a general point. The amplitude is over here. Make sure your diagrams make sense. So this is the amplitude. Amplitude is 0.2 meters. This is the center of the SHM. This is the natural length. This is E. Okay. So you can see now at this point, I have not drawn the object at the amplitude. So since we are about to prove the equation x double dot equal minus omega square x, I will be considering the object at a general point. So general point means how do you show it's a general place? I have marked the object somewhere in between the center and the amplitude. And then the distance that the particle moves from the center is what we mark as x away from the center. So away from the distance, this is x. So mark all the forces. What are the forces we have over here at this point? You have the weight, 0.5 g, and you have the tension. So guys, you know what you should do? Apply F equal ma at this general point. Okay, let's get it. Okay, so let's apply F equal ma away from the center. Okay, so away from the center we have 0.5 g minus tension equal mx double dot. Okay, so what about the tension? We know tension is equal to lambda x over L, right? So lambda is elasticity 50, x is, okay, how much is the extension? The extension in the sense, you know, I have told you several times now, the x here does not represent the same x we have marked in the SHM here. Okay, the x here represents how much the the spring has stretched beyond this natural length. So beyond the natural length, how much has it stretched out? E plus this x. So that's really important. Okay, so it's E plus x divided by natural length. Okay, so let's input that value. So 0.5 g minus tension, that's 50 into E plus x over L equals mx double dot. Do we know the mass? Mass is 0.5, right? So let's expand the bracket 0.5 g. I will expand the bracket with minus 50 over L. Can you see? So I will expand the bracket with minus 50 over L. So minus 50E over L minus 50x over L equals 0.5 x double dot. Yes. Okay, so now I think you can see I told you previously also now the E value. We actually have the exact value of E. Or else I think you can see that we have here 50E over natural length. Can you see? 50E over natural length is 0.5 g. So this is something that we got from the previous part, 50E over L. Can you see 50E over L is 0.5 g so that we can perfectly cancel it out. Okay, so now we can cancel out the 0.5 g. So 0.5 g cancels and we get minus 50x over L equals 0.5 x double dot. X double dot equal minus 50x over 0.5 L, right? Do you agree? Okay, so now let's simplify. 50 over 0.5 is a natural length also we have the value, right? Natural length is also actually how much? 0.5, right? Natural length is also 0.5. So 0.5 into 0.5. What is the answer? X double dot equal. X double dot equal. What did we get? Minus 200x. So x double dot equal minus 200x. Therefore, the particle moves in simple harmonic motion. Okay, so periodic time is 2 pi over omega. 2 pi over omega is, so omega square is 200, right? Omega is root 200. So let's give the value in the cal without giving the pi. Okay, so you type 2 over root 200 and you get root 2 over 10, and then you give the pi on your own. Okay, so if you type the pi in the cal, you will get a decimal answer. Okay, so in this way you can get a exact answer. So this is the periodic time taken for the simple harmonic motion. Okay, and then they say calculate the period of the resulting oscillation. That's done. Part C, calculate the maximum speed. Where do we always get the maximum speed in SHM? Always you get the maximum speed at the Vmax is achieved at the center. You get the Vmax here. Okay, so how do you get at the maximum speed in the equation? The x is 0. The x value here is 0. So all we have to do to get the maximum speed is what? Use v square equal omega square a square minus x square. Do you agree? So v max omega square is 200. Amplitude do we know? Yes, I think I have marked at the very beginning. Amplitude is 0.2. So amplitude is 0.2 minus x is 0. So v square equals 200 into 0.2 square, which is how much? 200 into 0.2 square. V square is 8, which means v is root 8, or in other words, v is 2 root 2 meters per second. So this is the maximum speed. Okay. We need to do more questions because there are more theory parts regarding this. Okay, so this is not over yet. We need to discuss more theories. Let's move to more questions now. Okay, so next we'll move to question number 5. A light elastic string. Okay, so this time we are working with a string. Okay, so be cautious of natural length 40 centimeter, or in other words 0.4 meter, has one end A attached to a fixed point. A particle P of mass 0.4 kilogram is attached to the free end of the string and hangs freely in equilibrium vertically below A. The distance AP is 45 centimeters. So can you see natural length is 40 centimeter, and now the string is 45 centimeters. Why is that? Because the particle is hanging. So because of the particle, the string has stretched 5 centimeters. Can you see that? So let's draw this. So when I draw my diagram, the natural length, I will draw this in one go. So this is the natural length. This is the natural length 0.4 meter. Okay, and the extension is now 0.05 meters. The extension is 0.05 meters. Okay, so this is the particle. Okay, so the extension is why? Because of the weight of the particle. They are asking you to find the modulus of elasticity. How do you find the modulus of elasticity? So consider the forces here: tension, and this is 0.4 G. So let's make them equal to each other. Tension is equal to 0.4 G. The tension is lambda x over L equals to 0.4 g. Lambda is unknown. X is the extension of the string 0.05 over natural length is 0.4 equals 0.4 g. So get the lambda value 0.4 g into 0.4 divided by 0.05. How much is the lambda value? Okay, right? How much is the lambda value? 31.36. 31.36 and we give the unit in newtons, right? The constant. Okay, so moving on to next part. The particle is now pulled vertically downwards until AP measures 52 centimeters and then released from rest. So guys, what's happening now? Currently at the equilibrium position, the this is 52. This is 45 centimeters, right? So what are they saying? The particle is pulled downwards until AP. Okay, until AP. So this is point A. This is P. Until AP measures 52. So how much are we actually pulling this? If AP is measuring 52 centimeters, from 45 to 52, to make it 52, how much are we actually pulling? We are pulling 7 centimeters. Guys, are you with me? So if you're pulling 7 centimeters, yeah, 0.07 meters, you're pulling it down. So if you're pulling 0.07 meters down below the equilibrium position, it means that is the amplitude. Okay, so let's draw another diagram now for the amplitude. So this, and remember when I'm marking the diagram, I will be marking the object in a general place. Okay, so first this is the natural length. I'm drawing a series of diagrams. Natural length is 0.4 meter. E is 0.05 meters. And over here, I'll mark the amplitude. Amplitude is, what was the amplitude? 0.07 meters. Guys, do you agree with the amplitude value? Because they say they are releasing the particle when AP is at a distance 52 centimeter. 52 centimeter means now from the point A to the equilibrium position, it was 45 centimeters. So 52 means from 45 to 52, that's a 7 centimeter difference, right? So that means you are pulling the particle 7 centimeters down below the equilibrium position, which means the 7 centimeter or the 0.07 meter becomes the amplitude. So now I have marked the particle not at the amplitude but at a general point. You know the rule. So this is the center of your SHM. This is the center of the SHM. The equilibrium position is the center of the SHM. Okay, the equilibrium position is the center of the SHM. And now I will be taking a general position and I will be marking F equal MA away from the center. Is this okay? The X is, in this case, X is the distance displaced away from the center of the SHM. So now use F equal MA away from the center and prove the SHM characteristic equation. X double dot equal minus omega square X. Okay, so let's do that. Okay, so let's apply F equal MA away from the center. Okay, guys, do you see there's one more interesting thing here? Before I go to apply F equal MA away from the center, do you see that they have used the word show that while the string is taut, P moves with SHM? Do you see the word? What do you mean by string is taut? Now you do, now look at this. Look at this question. Now you can see the natural length is 0.4. And you can see due to the weight, the equilibrium position is 5 centimeters below the natural length, right? And then we are pulling this a further 7 centimeters. The amplitude is 7 centimeters. Now, what's the rule? The rule that normally in SHM, you are supposed to go an amplitude below the center and an amplitude above the center. But you know the strict rule when it comes to these strings, the SHM, you only perform SHM while the string is taut. Now look at this. What's the issue? You can see below the center, okay, we can go 7 centimeters, that's okay. But what about above the center? Above the centimeter, do you see that the string is only taut for 5 centimeters? Can you see that the string is only taut within these 5 centimeters? So after it passes when it reaches the natural length, the string will actually become slack. So the moment the string becomes slack, will it perform SHM? No. So it will start to move like an object moving freely under gravity. So we will be doing more questions about that in the next. We will do questions regarding that part in the next part, in the next question. So at this point, what I want to emphasize is that this particle, will it perform complete simple harmonic? Will it perform complete SHM? No, the particle will not perform complete SHM, because to perform complete SHM, we need to be able to go one amplitude below the center and one amplitude above the center. But you can see that the string is only taught for 5 centimeters above the center. We can't go for 7 centimeters. So basically, the moment you reach 5 centimeters here, the string becomes slack and you stop performing the simple harmonic motion. Therefore, we don't have complete SHM here. Is that clear? So one thing, please make a note of this, write down. The amplitude is greater than E. Therefore, P does not perform complete SHM. It only performs partial SHM. Okay, it doesn't get to do the complete simple harmonic motion. Okay, is this clear? So this is really important. It's the in order to, so what's the requirement to perform complete simple harmonic motion? So if A is less than or equal to E, the requirement is if A is less than or equal to E, the particle moves in complete, or the particle moves, performs complete SHM. Is this clear? So this is really important. Okay. So anyway, this is not what's required here. What's required here is to show that the particle moves with SHM. Okay. So how do you prove the particle moves in SHM? You consider the particle at a general point. Can you see? And we apply F equal. And we apply F equal limit. So this is the extra note that I gave you guys away from the center. So what are the forces? So we have here. So we have the weight. Zero 0.5 G, and up we have the tension. So tension 0.5 G minus tension equal mx double dot. Guys, are you with me? Mass is given, right? Mass is 0.5. Let's input the mass as 0.5. 0. Mass is 0.4. Oh, sorry, 0.4. So this is also 0.4, right? So this should be 0.4 G. Okay, so 0.4 G minus tension is lambda x over L. Let's input the values. 0.4 G minus lambda value. Let's keep it for it now. Lambda extension is how much? So in here, again, I keep telling this in every question. The x here does not represent the same x we have here. This x here representing Hooke's law is the amount the string has stretched beyond its natural length. So beyond the natural length, the string has stretched E plus x. Agreed? Divide by L. 0.4 x double dot. So you get here 0.4 G minus lambda E over L minus lambda x over L equals 0.4 x double dot. So I get here 0.4 G minus lambda E over L is, guys, can you see lambda? E value here is 0.05, right? Let me just show it to you. And natural length is 0.4 minus lambda x over natural length is 0.4. Guys, do you see something here? You can see here lambda into 0.05 over 0.4 is how much? This is 0.4 G. So 0.4 G minus 0.4 G minus lambda x over 0.4 equals 0.4 x double dot. 0.4 G, 0.4 G cancels out. Replace the lambda value as 31.36 minus 31.36 or x divided by 0.4 into 0.4 equals x double dot. So x double dot equal minus 196 Okay, so this is the characteristic equation. So you can say therefore P moves in simple harmonic motion. Is this clear? Part C, they are saying find the period and amplitude of the motion. So amplitude of the motion is already seen, right? Amplitude is 0.07. What about the period? What about the period? Period of the motion is equal, period equals to 2 pi over omega. Guys, what's omega? Omega is root 196, right? Omega square is 196. How much is root 196? 14, which means it's pi over 7 seconds. And amplitude? 0.07 meters. Is this clear? Okay, then let's move to the other part. Last part. Okay, look at this. Part E. Find the time taken by P to rise 11 centimeters from the point of release. Okay, how do we find the, sorry, that's part E. We have moved to part D first, right? Find the greatest speed of P during the motion. How do you find the greatest speed? Greatest speed is at the center. You know the greatest speed is at the center, Vmax. Vmax is achieved at the center, and you know at Vmax, X is 0. So let's do that part C. V square equal omega square A square minus X square. So Vmax, omega square is 196, amplitude is 0.07 square, X is 0. Guys, how much is it? 196 into 0.07 square. 196 into 0.07 square is 0.9604, and square root that. That's an exact figure. So velocity is 0.98 meters per second. So that's the maximum speed. Okay. Okay, let's try the part E now. Find the time taken by P to rise 11 centimeter from the point of release. Guys, how do you find the time taken by P to rise 11 centimeter from the point of release? Okay, so how do you find the time taken by P to rise 11 centimeter from the point of release? Now, the first thing is, where do we release this? Where do we release this? We release this at the amplitude, at the very corner. So from the amplitude to come to the center, how much of a distance are you moving? 7 centimeters, 0.07 meters. And then, now they want us to find the time taken to rise 11 centimeters from the corner. So then, since you have climbed 7 centimeters to the center, from the center, how much more do we require? Well, yeah, so 7 centimeters covered, another 4 more centimeters. So if you are covering another 4 more centimeters, my question is, are you within the range of the simple harmonic motion, or are you going to the place where the string becomes slack? So are you in the range where the string is taut, or do you go to the range where the string is slack? You are in the range where the string is taut, because you can see above the center, the string is taut for 5 centimeters. So we are going only a 4 centimeter, which means you can apply all the SHM rules. You can apply all the SHM rules to find the time taken to go from where to where. At this point, you are at the very corner. From the corner, 4 centimeter above the center. Guys, can you see? So we need to find this time. We need to find the time taken to go from the amplitude to 4 centimeters. Guys, are you with me? To 4 centimeters above the center. So how do we do this? There are several ways of doing this. I have taught you several ways in the very first exercise concerning SHM, how to find the time. So there are 2 ways. I have taught you a shorter way and a longer way. So what's the way? The first one, if I say the longer way, what is it? So if I just draw a quick sketch over here, this is part E, right? So this is the particle. This is the 7 centimeter, the amplitude. This is the amplitude, that is 0.07 meters. And this is the highest point P. So at this point, X is 0.04. So I want the time taken to go from A to this point. So how do we find the time taken to go from the amplitude to the center? Amplitude to center, the time taken is what? A quarter of the periodic time. Do you recall? The time taken to go from the amplitude to the center is always a quarter of the periodic time. Isn't it? It's a quarter of the periodic time. Okay, and then from the center to go to this particular point, to move 4 centimeters away from the center, what can we use? How do you find the time taken by the object to move 4 centimeters away starting from the center? What's the equation we use? We can use x equal. What equation do we use? We can use x equal a sine omega t. So this is the short, the longer way. So x is 0.04, amplitude is 0.07, sine omega is 14 times t. So we get here 0.04 over 0.07. So sine inverse 4 over 7 equals 14t. T equals 1 over 14 times sine inverse 4 over 7. Guys, are you with me? And then the total time. So this is actually the longer way. So total time is a quarter of the periodic time plus 1/14 of sine inverse 4 over 7. Periodic time we just found, right? Periodic time was pi over 7. So 1/4 of, because t over 4 is 1/4 of pi over 7. Plus 1/14 of sine inverse 4 over 7. Guys, how much is this answer? Let's type it in the calc. Give me the answer to 3SF. So the answer is 0.15564, it goes on. Okay, so 0.156 correct to 3SF. So this is the longer method. Guys, can you remember the short method? What's the short method? Yeah, you know, if you are starting your motion from the amplitude, you can use x equal a cos omega t. And remember, x value is measured from the center. So if you are going now, you're starting from the down, you're starting from below the center, and you can see your particle is now above the center of excitation. So when you pass the center and go to the other side, x should be positive or negative. X should be negative. So above the center, it has gone 0.04, so negative. Okay, so I have explained this in the previous exercise. Cos omega t, so 14t. If you do this, you can immediately get the answer. Cos 14t, and then this is cos inverse. 14t equals cos inverse minus, actually this is 4 over 7, right? 0.04 over 0.07 is 4 over 7. T equals 1 over 14 times cos inverse minus 4 over 7. So this should give you the answer immediately. You don't need to go in 2 steps. Actually, you can get the answer in 1 step. Guys, can I know how much it is? Do you get the same answer? You need to type it in the calc. Check whether you get the same answer. Yes, right? You should get the exact same answer, 0.156 seconds, correct to 3 significant figures. So you must get the same answer. Okay? This is clear? Okay, so now we'll move to question number 6. A particle P of mass 0.4 kilogram is attached to one end of a light elastic string of natural length 0.5 meter and modulus of elasticity 10 Newton. The other end of the string is attached to a fixed point A and P is initially hanging freely in equilibrium vertically below A. The particle is then pulled vertically downwards a further 0.2 meter and released from rest. Calculate the time from release until the string becomes slack for the first time. Okay, so there's a lot to do here. Okay, what's the first thing to do here? First, let's draw the object in the equilibrium position. So how is it in the equilibrium position? At the equilibrium position, first, you have to mark the natural length, which is how much? Natural length is 0.5 meters, right? And what about the extension is not given to us, right? So here we have the tension and here we have the weight 0.4 g. Shall we make them equal now? So you have to do the previous process again. Tension is lambda x over L equals to 0.4 g. Lambda is 10 into extension x is E, right? Over natural length is 0.5 equals to 0.4 g. So E equals 0.4 g. Actually, you could keep it like this. We don't need to find the E also. All I need is this relationship because when we apply F equal ma at the general point, we are going to use this as a substitution, isn't it? That's what we are going to do. Okay, and we'll write this down 0.4 g into 0.5 divide by 10. Okay, so guys, let's move. So the next step that you need to do is to draw the particle at a general point. So what do you mean at a general point? A general point is something that is so over here. This is the natural length. This is the equilibrium position. Can you see this is the equilibrium position? This is the equilibrium position. And let's say this is the amplitude. Guys, do we know the amplitude by any chance? Have they given us? The particle, they say, is then pulled downwards a further 0.2 meter and released from this. Can you see? So they are saying they are pulling it down a further 0.2. So actually, I'm interested over here to see whether this E is actually bigger than 0.2 or greater than, smaller than 0.2. Can I actually have the E value? How much is the E value? 0.4 into 9.8 into 0.5 divided by 10. How much is the E value? Because I want to check whether we have complete SHM here or not. It's 0. 0.196, right? Yeah. 0.4 G, 0.4 into 9.8 into 0.5. This is the 0.4 G, right? It's not 0.49, 0.4 G, 0.196. So I think guys, you can see the E value is 0.196. And I think, and you can see that the distance that you are pulling below the equilibrium position is 0.2 meters. Guys, can you see? So the amplitude is 0.2 meter, and you can clearly see it is a larger value. Okay, so the amplitude is comparatively larger. Okay, so then I'll first thing we'll do is we'll mark the particle at a general point, take the particle at a general place, and what do? We apply F equal ma towards the away from the center. So the x is measured away from the center. X is measured away from the center. So this is the tension, this is the weight. So let's apply F equal MA away from the center. So what do we get here? 0.5 G minus tension equal M times X double dot. Do you agree? 0.5 G minus tension is lambda X over L mx double dot. Lambda is 10, right? Into X is E plus X. Guys, by now you know the extension is the length the string has stretched beyond its natural length. So beyond the natural length, it has stretched E plus the X amount divided by natural length is L. Natural length L 0.5 equal mass is 0. 0.4. I keep using 0.5. Why is that? I keep using this 0.4, right? Yeah, I keep using 0.4. So this is 0.4. I need to fix that. Mass is 0.4 into X double dot. Guys, do you agree? So 0.4 G minus 10E over 0.5 minus 10X over 0.5 equals 0.4 X double dot. And then guys, can you see 10E over 0.5 is how much? 10E over 0.5 is actually 0.4 G. This is equal to 0.4 G. Are you with me? So 0.4 G minus 0.4 G minus 10X over 0.5 equals 0.4 into X double dot. 0.4 G plus minus and plus cancels out. Minus 10X over 0.5 into 0.4 equals X double dot. How much is the X double dot value here? Minus 50X. So X double dot equals minus 50X. So this is the equation, and therefore you can say what? Therefore particle moves in SHM. Okay, so we just proved that the particle moves in simple harmonic motion. However, the question is calculate the time of release until the string becomes slack for the first time. So guys, now the first thing here is you saw that the amplitude is greater than the E value. So what does that tell us? If the amplitude is greater than E, do we have complete SHM? Or do we have only a partial SHM? We have partial SHM because the amplitude is greater than the E value. So therefore, the particle doesn't perform complete SHM. Remember, SHM is only performed while the string is taut. Okay, particle performs partial SHM. Partial SHM means it only performs SHM while the string is taut. Okay. Now they are asking you calculate from the time of release. You know you're releasing it from the con amplitude, right? They are asking the time until the string becomes slack for the first time. Where does the string become slack? The string becomes slack. Now you know this is the center of your SHM, right? This is the center of your SHM. So where does the string become slack? It becomes slack when it reaches its natural length. Guys, so when does it reach its natural length? When it is a distance E away from the center. So guys, can you see if I use X as E, I can, how do I get the time? I mean, how do I get the time taken to go from the con amplitude to this point over here? What equation do I use? I can go with SHM, right? Because from here to here, it moves while the string is taut. So what equation can we use? We can go for the shortcut, right? X equal A cos omega t. And you can use X as negative because it passes through the center and goes to the other side, right? So shall we use that? So using X equal A cos omega t. X is the E value, but you should remember you should use the what? Positive value or negative value. You must use the negative value. Amplitude is 0.2. Cos, what's the omega value? Omega square is 50, so omega is root 50. minus 0.196 divided by 0.2 cos root 50t. So root 50t equals to cos inverse minus 0.196 divided by 0.2. So t equals to minus 0.196 divided by 0.2. Okay. So let's get the time. How much is the time taken? 0.4159. It goes on. So correct to 3SF 0.416 seconds. Okay. Okay. So now we'll move to part B. They say calculate the time between the string first becoming slack. First becoming slack is, I think you saw when it reached the natural length, right? When it reached this point. And the next time it becomes taut. Guys, when does the string become taut again? Now you know the particle, you release it from the amplitude. It comes increasing in speed until it reaches the center. At the center, it reaches V max. And then after that, it goes to the other side, decreasing in speed, and then it reaches the natural length. The thing is, it's not capable of going for the full amplitude because before going to the amplitude, you reach the point where the string becomes slack. So then at this point now the SHM motion stops, and what happens? I told you previously, the moment the string becomes slack, the particle starts to move as an object moving freely under gravity. So M1. From this point onward, your particle is going to move freely under gravity. So then when does the particle become taut again? Now, if it starts to move up here as an object moving freely under gravity, when does the string become taut again? You know, it doesn't go up forever, right? It will go up until the velocity becomes 0, and then it starts to come down. And then when does the string become taut again? The moment it reaches the natural length again. Guys, can you see? So from the moment the string first becomes slack, that's at the natural length, it will go up as a particle moving freely under gravity, and it will come down again, and it will come back to the natural length, and immediately the string becomes taut again. So basically, they are asking you to find what time here? They are asking you to find the time of flight where the particle is moving freely under gravity. Do you see what they want you to do here? They want you to find the time where the particle is moving freely under gravity. Okay, so how do we find that time where the particle moves freely under gravity? How do I get that time? The first thing you should do here is you must first find the speed, because we need to know the initial speed of projection for the part where it's moving freely under gravity. Guys, are you with me? So this is the particle and this is the natural length. At this point, I need the speed. Are you with me? Because from this point onwards, the string becomes slack and the particle moves under gravity. It goes up and it comes down. Guys, are you with me? The particle will go to a point where the speed is 0. The string is completely slack and it will come down. And when it reaches its natural length, the string becomes taut again. All you got to do is to find this time. So let's find the time. So guys, to find the time taken while the string is slack, all you got to do here is what? Now the thing is, we don't know how much of a distance this moves forward from this point. Okay, this is the natural length. Okay, so thing is, okay, after it passes the natural length, it comes to the natural length with some kind of a speed, and then the string becomes slack, so it will move a little bit of a distance upwards until the velocity becomes 0 and it comes down. And when it comes back to the natural length, the string becomes taut again. Your task is to find the time taken for the particle to move while it is moving freely in air. So what you need to do here is basically you need to apply V equal U plus 80. You could apply V equal U plus 80 from here to here. At the highest point, velocity is 0. Find the time taken to go half of the journey. And then simply multiply that answer by 2. Use V equal U plus 80. Find the time taken to go to the highest point. and multiply that by 2. So you can see the only thing that you don't have here is the v, because you know the particle moves freely in air. The acceleration is 9.8 g, right? All you need to find is the speed of reaching. You need to find the speed with which the particle reaches the natural length. At this point, what is the speed? Guys, are you with me? You have to find the speed at this point. What is the velocity? What's the speed at this point? Okay, so how do we find the speed at this point? So you can, until this point, it moves under SHM. So we can use what? V square equal omega square a square minus x square to find the speed that the particle reaches this point. So the x value is how much? In V square equal omega square a square minus x square, what is the x value? How much of a distance has the particle moved away from the center? How much of a distance has the particle moved away from it? It's not on the center, right? It's over here. So how much of a particle distance has the particle displaced from the center? This E value, right? It's not on the center now. Remember, it's not on the center. It's over here. If it is on the center, you get V max. Right now, we are not on the center. We are at this point over here. So the X value is 0.196. Okay, so let's use that. So we'll apply V square equal omega square a square minus x square. So I want to find the velocity. Omega square is 50, right? Amplitude was 0.2. We have already marked it. Minus x is 0.196 square. Guys, let's type it in the cal, get the answer. So let's find the speed with which this particle reaches the natural length. How much is it? V square, we get here 99 over 1250 or 0.0792. And then square root by, and then let's root it to get the V value, root answer. We get 0, so I'll write the full value. Root 0.0792 and I get 3 root 22 over 54. Now let's go with the full figures, okay? We'll go with the full figures, and at the end, if we use G as 9.8, we should give the answer to 2SF or 3SF. Okay, and then and then let's apply the equation. So I have the speed with which the particle reaches the natural length. That speed becomes the initial velocity when the particle moves freely under gravity. Are you with me? This speed that you obtain here, that speed becomes the initial speed when the particle moves under gravity, freely under gravity. When the string is completely slack, this V that you found becomes the initial speed. So all you got to do now here is what? Apply V equal U plus AT. So at the highest point, V is 0, U is the 3 root 22 over 50, the speed with which you reach the natural length. We are applying this upward, so the acceleration G is minus 9.8, isn't it? So we get here plus 9.8 T equals 3 root 22 over 50. Guys, you understand why I use minus 9.8 here, right? We are applying the equation upwards. This is M1. So T equals 3 root 22 over 50 into 9.8. But this is not the time we require because this is the time taken to go from this point to the highest point. I am supposed to find the time taken for the string to become taut again. So then string becomes taut again in how much of time? The string is taut again with in how much time? 3 root 22 over 50 into 9.8 times 2, right? Because you have times the time by 2 because that's the time taken to go up. You have to come back down again for the string to become taut. So multiply 3 root 22 over 50. That you should divide by 9.8 and multiply by 2. So how much of a, what's the time value we get here? Yeah, let's type this in the cal, get the answer. So it's 0.0574 2857. It goes up to 3SF 0.0574 seconds. Corrected to 3SF. So this is the answer. Okay, is this clear?